little background. A couple months ago, about 2.5 months ago, we were on our weekly ASCENT call, and it came up that there might be an opportunity for a 3U launch next year because we couldn't do CQC, and would we have anything to launch, and what would we do? So we kind of talked about what's possible.
A little bit of light, right?
Yeah, so we kind of talked about what's possible. And so this is kind of an outcome. So I'm going to give you a little words and maybe what's possible. And then I put together a demo over the last 2 months of both the satellite, there's two SDRs in this satellite, and then 2 SDRs on the ground also. And so what it could do and why would we do that. And just as a background, the big picture, I say this, is we really want to do things like more than just an FM satellite for the future. We'd really love to do digital modulation. Michelle will talk about in the slot this afternoon. So the only issue is not quite done yet. Looking good, but not quite there. So next year, that's soon, right? Even the year after is like pretty soon. So we'd still want multiple channels. We'd still want to utilize our bandwidth. We want to try to overcome some of the problems of, let's say you had multiple users. One guy had high power, one guy had low power. Is he going to take over the satellite? Is it going to modulate everybody? We want to try to get rid of all that, right? So you can go in and make it multiple channels. To do that, and that's the sharing part. The downlink, I'm still going to assume it's going to be on X-band. And again, SDR, very programmable. I've got it set up back there right now for 10.2, more in the experimental frequency right now. But it can program the whole band. And you really need real-time Doppler compensation because when a pass comes over, you could have plus or minus 250 kilohertz of Doppler at X-band. Pretty significant. So your TLE would help, but really the way to do it is to track the Doppler itself. So what I do is I transmit a pilot tone going down there. You know, it takes some of the resource of the satellite, but at least you can always track it. So you always know where you're at. Okay. A lot of words. As I said, really like this, but not there yet. These are kind of our current goals. It's in the paper. General approach, basically using GNU radio, but now the link is in the paper again, like the other one for the source code. But again, if you're not into GNU radio, no big thing. I'm not going to talk about it here in the demo area. If you want to talk about GNU radio, I'll be happy to. But I'm just trying to get the more system, how would you use this as a station? So I use an Edis N210 and a RTL dongle for each of them. Actually, the setups are identical in that respect. It could be a satellite, it could be a ground station. The only difference is for the satellite one, since my SDR, the one I have here only goes up to 4.5 gigs. So to get up to X-band, I need an external mixer. So I use an RF Explorer with a 6 gig source. I just beat it up. Works fine. For the ground station, not only do I use these two, but I use a Avenger LNB. Again, for 20 bucks, you can't beat the cost. So on the receive side, an LNB and RTL dongle is all you need, right? In the program, and you can receive the data, right? So that's the setup. Right now, it's set up so the satellite can listen to all these bands. As I said, it's set up to just transmit down at 10 gigs right now. And I have a local one hooked up. That's what the other SDR is down here is, because it was easier than having a mic. You just use an HT as a mic. So the other goal, and I have done this at 5, so this easily can be 5 and dime. I mean, at my house, I actually do use the 5 more than this. Let's see, other things that I didn't quite mention before, but maybe I should add in here before I forget, is that scientific package. So I'm not going to talk about what could be a scientific package, but one of the things is it could be ham radio, for instance. We could scan the bands. We could scan the bands all the way from, a couple hundred kilohertz up to 5 gigs and show you what was around. So the idea would be to scan the bands, store it on the radio. I don't know about downloading all the data to your database, but it would be essentially just like you looked at an FFT plot of the data, and it's not a problem as far as data rate. Really, at 9600 baud, this would be very fast. In fact, you could probably do it at 1200 baud. Now, the satellite that I have in the back is good for plus or minus 128 kilohertz. So really, 9600 baud is really not an issue. So anyway, that's before I forgot. Block diagram, you'll see that. This is all built in the back. And again, for debug purposes, I use the SDR console, worked pretty good. So this is the type of thing you could do. Again, the whole idea is it's programmable. You could easily change this. You could upload the code and make it a completely different satellite. In this case, I allowed some for the digital, and then I allowed for a couple of narrowband FMs, PSK31s, some upper-lower sideband, and in fact, in the back you'll see in the demo that I have a CWID beacon going at 30.5 kilohertz separated from the main carrier. I have decoded with I think I'm using an upper sideband. I have a narrowband FM going on. I have 4 PSK31s, and since I can't type that fast, I just put ID information into it. So it kind of works. So here's a picture of the spectrum when I first started. It seems like a long time ago, 2 months ago. Anyway, this is the noise in the digital portion, and that's the carrier for the narrowband FM. And I turned off every other major channel. This is actually a ranging pseudo noise thing and a carrier for it. For Cube Quest Challenge, we had a requirement of measuring range at 1 million kilometers. So we developed a waveform to do that, and that's part of that. So again, this is an example of the channel breakdowns, where we have on each channel, we could have an AGC, a squelch, translated up and down, no matter where it was received, and no matter which band. So for the demo, I have received right now, I think I'm set up on 2 meters going up and 432 going up from the ground station. But really, it could be anything. I have L-band going into the ground stations in my input, just because I didn't want to, frequency interfere with each other. But we can mix and match in here. You can have frequency channelizers. You can have BPSK. Really, no matter what you want to think of, you can have. And then you weight them all. And the reason you want weighting on the output, also what I don't show is the limit. So if you try to push too much power into it, no matter what you do, sorry, not going to get out the output. So to discourage people from doing that, it'll just distort their signal, which they won't like. So they'll be forced to turn down their signal. So you want to weight the output, because when you have multiple carriers of whatever modulation, there's going to be some issues, no matter how well you filter it over here in the amplifier. And so you don't want somebody coming in with a very, very strong signal that's going to try to grab all the power and screw everybody up. So you could have a very efficient waveform like PSK31 is pretty efficient at 31 hertz, or CW, very efficient. So they don't really need the power that they could use. And some other waveforms might need more power. So you really want to weight the output. We're just trying to address some of the issues that one would have. Now in the ground station, of course on this development of this, I did this in a kind of cyclic development cycle. So I did it in 5 loops, if you will. So if you look on the website, you'll see SAT test 1 through 5. So SAT test 1 has just basic capability. 2 has a little bit more, 3 has a little bit more, 4 has a little bit more, And 5 is, well, you better have a pretty good computer because it's going to start to have issues. So I did that. Now demo's only up to demo ground test 1 and 2, Rev 2 of 2, but still down to 2. So it does basic things like it has a transmitter on the uplink. You'll display the frequency. It has the frequency lock circuit in it, although not exactly tuned up. And it certainly can receive local information, like on, I have it set up for now on 5.2 on 2 meters. And you can channelize it in there and upload the FM data. And then all the data, and you'll see the whole frequency plan coming down at you. So on the 2 computers, on one you'll see what it sent and through X-band, and I have an X-band link across it. And on the other one, you'll see what's received. So the whole demo is about how to use it. You know, what it would look like. You know. So it looks like I have a little time. So this is the science experiments that are possible. Really, you get hams thinking about this. The possibilities are kind of endless. Second receivers, you could have emergency channels. You could look at the ionosphere from the top side, not from the bottom. So not the reflections that you might see, but can signals on the low bands get through? Remember, if they can't get through, where do they go? Either they're ducted or reflected. So it's just another way to do propagation. Not exactly the way you're used to determining the maximum usable frequency. It's just another way. Something we could look at, which I don't think we've done before. Automatic logging of users, peak users, satellite detection. And I talked about this, how long it would take if you had all this data to downlink it, because you could do it as an image, so which would actually be faster. You could compress it up in the satellite. But these satellites are pretty small in reality. The whole radio is inside of an FPGA. So I'm showing it on laptops, but a real SDR would probably all be programmed within the FPGA, way more efficient, and would work much better than the demo I have back there. So these are things to think about when we can't find somebody else to pay the freight, or if we can convince them that we're the science for somebody else. So go see the demonstration. These are the tests. This is what I add. This is the basic one with a linear repeater, a CW tone, an ID tone, and I also have it for a pseudo Doppler and a test rack. So what these are used for is when you build one of these simulations, the first thing you want to do is you want to have a way to test it. So you actually build in some test equipment inside, a sweep oscillator, a noise generator, things like that, and you switch between them. So you have your circuit, which is all in software, and then you can turn on a sweep generator or an oscillator, move its frequency, and see how your circuit performs. And that's a good way to do it. By the way, all my stuff has notes in it and frequencies, all up on GitHub. It's all within the graph. Looks kind of messy, but works for me. So then I added certain things, and if you have a very low-end computer, like even lower than a Raspberry Pi, like the first Pi, this would run fine, right? As you get on, you're going to need more of a computer, and as I said, by this time I have 36 channels running, 30 of them with 2 kilohertz bandwidth, 6 of them with about 7.5 kilohertz bandwidth. I have 3 PSK31s, IDs, grouped together in one channel, one PSK31 high, regular CW1, a narrowband FM. I have the ranging thing. I have it turned off in the back. So there's lots of stuff in 5, enough to choke any computer. So these are the things you'll see, and I have them up on the board. Where they are. This is the CW carrier. This is a narrowband FM with no modulation. This is the ID tone going on. And up at the top, it shows you what this is from number 2, for instance. And this is the pseudo Doppler tab that you can set. So you can set it to Leo or whatever you want, and it'll show you the Doppler and how much show you the modulation. Set the squelch on both sides. Turn it up too high and you put noise in, well, you're going to get noise out. You can change the gain at the bottom. Let's see. So I have local input received, shifted over here to one of the other channels so you can get multiple voice channels. Let's see. So the top one is a zoomed in of the bottom one. And the reason you need that is if everything's locked, this is great. And you can actually highlight the area you want with your mouse and zoom in even further. But as it turns out, with the vast Doppler you have, you're going to want to see it zoom through with this big picture waterfall. And you can zoom in and out of this one also. That's the reason for 2 zooms. And there's the reason. Okay. Set to Leo, and you can see my simulation is looks more like a triangular wave instead of rounded. But in 10 minutes, it does that. It's pretty awesome. So here I show the 6 channels and where I stuffed in the PSK31s and the ID channel is over there. So I have a built-in noise generator. I turned on the noise generator, and now you can see the upper bank of 30 channels. So in this plot, you can see them over here. And what you can't see, well, I'll show you in a second, is the PSK31 here. There we go. So here's where I stuffed in the PSK31, and I turned off the noise. And this is in the upper channel. It's still there. So now you see it, and later on you don't. And here I show where the PSK31s are. And you can't see it in this one. It's there. You could decode it. It's just way up in the top. You can't even see it in here. It's actually reduced. The reason is the filtering that I'm using creates 32 filters, and one of them you can't use. It's got offset on DC. Another one is reduced to like 20 dB. Not a problem for PSK31. Yeah, it's down 20 dB. Yeah, receives fine. So, go see the demonstration.